Alright, so in this talk, we consider an information theoretic approach for unsupervised feature extraction. This is a joint work with my student Xiangxiang Xu and Professor Li Zhongzhen from MIT. Well, different from the supervised learning, it is generally not so obvious what kind of information we want to extract from data without the instruction by the labels. And it is even more unclear how the information theory could help designing unsupervised learning algorithms. So to get some intuitions here, let's think of how a typical unsupervised learning algorithm works. Perhaps the most widely used unsupervised learning algorithm is the principal component analysis, the PCA. Given a collection of data vectors, the goal of PCA is to select the principal direction that can describe the data vectors very well, and it is implemented by the singular value decomposition of the empirical covariance matrix. Intuitively, the selected principal directions by PCA captures quite a lot of common randomness shared between different dimensions of the data vectors. And in that sense, PCA could be viewed as trying to extract certain kind of common information between different parts of data. Then the question is how this intuition could be formalized by information theory in unsupervised learning. Here, as a real example, consider that in a smart building that we may have the photo data, voice data, and working vibration data from a person. And these data are in very different types, and using this data to predict the person requires to jointly analyze the multi-model data. In such problems, since different types of data are generated from the same person, which is the label and the common information shared by this data. Therefore, extracting low-dimensional representations about the common structure shared among this data could be useful for dealing with multimodal data analysis problems. Now consider another example, the emptiness problem, where we want to recognize the digits from the images. Typically, this problem is solved by the convolutional neural networks, where each image is divided by some subareas and then extract features for each subarea by the convolutional neural network. Note that the goal of these extracted features are to predict the digits in the image. So these features should all be informative about the digits, which is actually the common information shared among these subareas. Therefore, extracting the features for the subareas about this common information, this is essentially an unsupervised learning problem, could be useful for the original supervised learning problem for predicting the label. Now here is our mathematical formulation. Suppose that we are given a sequence of pairwise dependent discrete random variables x1 to xd with joint distribution px1 to xd, and assume that we can observe a sequence of sample vectors which are RID generated from the joint distribution px1 to xd. Our goal is to find the function f of x1 to xd so that this function can convey much information about the common structure shared among these random variables x1 to xd. We want to find this function from the observed data vectors. Then in order to find such function, we need to first define the notion of common information, which requires an information matrix to measure the commonness between random variables. And moreover, in order to apply to practical problems, the selected function has to be efficiently computable from the data. Now let's go through more details. Given discrete random variables x1 to xd, we apply the Watanabe's total correlation, or simply called the total correlation, to measure the common information shared between these random variables, which is defined as the KL divergence between the joint distribution px1 to xd and the product of their marginal distributions. Note that in the special case, when d equals to 2, the total correlation is reduced to the mutual information between two random variables. Then, for an attribute u of x1 to xd, with the conditional distribution px1 to xd given u, we look at the difference between the total correlation with and without given the knowledge of the attribute u, which by definition can be expressed in terms of these mutual informations. Then this measures the information reduction of the common information between x1 to xd with a knowledge of u, which can be viewed as the amount of information that the u contains about the common structure between x1 to xd. Therefore, we can formulate the information theoretical problem to select an attribute u to maximize the loss of the total correlation. Then this gives us an information theoretical optimization problem. Once we solve the optimal conditional distribution px1 to xd given u, we can then use the log likelihood function, which is a sufficient statistic to detect u, as the informative representation of the data about their common structure. However, note that this optimization problem is not well posed, since we can always choose u as a high-dimensional random variables consisted of x1 to xd, which maximizes the total correlation loss. Therefore, we need to put some restrictions on the attribute u. In fact, it was considered by Versteeg et al. That to restrict the cardinality of u, and the resulting approach is called the information sieve. However, the optimal features computed from the information sieve have no systematic structure, and it is hard to get theoretical insights from the optimal features computed from the information sieve approach. So in this talk, we want to restrict the mutual information IU x1 to xd to be bounded by a small epsilon square. This is a kind of information bottleneck constraint and should be more familiar in information theory. It turns out that such local assumption allows us to focus on the most significant low-dimensional features of the data about the common structure, which is often more useful, and more importantly, this local assumption give rise to a geometric structure for this information theoretical problem, which actually lead to a principal decomposition of the common information that we will show later. Before going further, note that with the local assumption, we can approximate the log likelihood function by the first order Taylor expansion to the relative likelihood function, since the conditional distribution is close to the joint distribution by the local assumption. And for simplicity of presentation, in the rest of this talk, we will focus on selecting the binary attribute u with the Bernoulli 1/2 marginal distribution, and the extension to the general attribute u is just straightforward. Now, in order to solve this optimization problem, we need the following notations. First, for each conditional distribution pxi given u, we define the so-called information vector psi associated to this conditional distribution, whose entries are the difference between the conditional distribution to the marginal distribution pxi scaled by epsilon times square root of pxi. Then we can similarly define the information vector phi for the joint variables x1 to xd, and we know that for each information vector psi I, the dimensionality is xi, and for the information vector phi, it is an x1 times x2 to xd dimensional vectors, which is actually in a very high dimensional product space. Moreover, the log likelihood function for the distributions condition on u can be written as the information vector scaled by the square root of px. So this introduces a one-to-one correspondence between the binary attribute, the information vector, and the log likelihood function. What is interesting here is that with the local approximation, by using the second-order Taylor expansion, the KL divergence can be approximated as Euclidean norm square of these information vectors. Therefore, we can reduce the information theoretical problem to a linear algebra problem where we want to maximize the norm square sum of these information vectors psi given the norm square of the information vector phi. Note that by definition, the information vector psi and phi are connected by a linear transformation bi, which is actually xi by x1 times x2 to xd dimensional matrix with entries specified by the square root of the joint distribution. Therefore, we can interpret this optimization problem as designing the unit vector phi in this input space. We want to choose the direction of phi in this space so that after the linear transformation b1 to bd, the output images have the largest total norm square sum. Also note that the linear transformation bi can be interpreted as a projection operator that projects the high-dimensional vector phi from the product space onto the low-dimensional spaces xi. Now, in order to solve this linear algebra problem, notice that if we stack the vectors psi as a very long vector, then the square norm of this very long vector is simply the sum of the square norm of all the component vectors psi. So we can write the sum of the square norm of this vector psi as the norm of one vector, which is the matrix B0 times the information vector phi, where the B0 is the matrix stacked by the matrices B1 to BD. Then the problem is reduced to designing the unit vector phi in the product space such that after the linear transformation B0, the output image at the stacked space with dimensionality x1 plus x2 to xd has the largest output image. Then the optimal information vector phi to maximize this output norm is simply the largest right singular vector of the matrix B0. Then, after the optimal information vector phi is solved, we can compute the desired functional representation of the data by the correspondence between the information vector and the log likelihood function. In fact, if we denote psi as the largest right singular vector of the matrix B0, and we divide this vector psi into subvectors psi1 to psi-d, where each subvector psi is an xi dimensional vector, then it can be shown that from the projection structure of B0, the optimal functions f of x1 to xd corresponding to the largest right singular vector psi is precisely the sum of the functions f1 to fd, where each function fi is the log likelihood function corresponding to the vector psi I. And note that although we didn't assume f to be in additive form, the optimal feature functions in our development intrinsically admit such structure. Therefore, although f is a very high-dimensional function, is in product space, it can be computed efficiently by specifying the singular vector psi, which is in an additive space, and we can compute each corresponding functions fi by dividing the vector psi into psi1 to psi-d and transfer to the functions by this correspondence between information vector and the log likelihood functions. And we can see that the dimensionality of the singular vector psi is in a dimension linear to the number of variables, which is in a much lower dimension and is easier to compute from data. Now, how do we compute the singular vector of the matrix B0? Note that computing the largest right singular vector of the matrix B0 is equivalent to compute the largest eigenvector of the matrix B0 times B0 transpose, which we define as the matrix B. And it turns out that, by definition, this matrix B can be expressed as a set of blocks Bij, where each Bij is an xi by xj dimensional matrix with the entries specified by the pairwise joint distribution of these random variables. Then we can apply the power iteration algorithm to compute the largest eigenvalue of the matrix B, which starts from an arbitrary vector psi1 to psi d, and then iteratively multiplying the matrix B to this starting vector. This can be summarized as the updating rule for each component vectors psi I. Because of the spatial structure of the matrix Bij and the correspondence between the information vector and the functions, these updating steps can be equivalently expressed as updating the functions of the data by the conditional expectation operators. Since the conditional expectations can be directly computed from the training data, this gives us an algorithm to compute the desired functions from data, which we call as the multivariate alternative conditional expectation algorithm, or simply called the Maze algorithm. In addition to the largest eigenvectors, we can further compute the top k eigenvectors of the matrix B, which corresponds to the top k informative features about the common structure. And in practice, this can be easily implemented by the Maze algorithm with the Gram-Schmidt process to decorrelate the computed functions with respect to previously computed functions. Now to see how the Maze algorithm can be applied to unsupervised learning problems, let's look at an example where we have a sequence of binary independent bits b1 to bn, and each random variable is composed of a subset of these bits. For example, we could have the random variable x1 is composed of b1, b2, b3, and x2 is b1, b2, and x3 is a bit b1, b3, and x4 is simply the bit b1. Then, the Maze algorithm actually computes the bit patterns that appears the most of times among these random variables. In this example, the pattern b1 appears 4 times among these random variables, and the largest eigenvector corresponding to this pattern, with the largest eigenvalue being 4, which is the number of times this pattern appears in these random variables. Moreover, all the eigenvectors of the matrix B represents different bit patterns, and the corresponding eigenvalues count the number of times that this bit pattern appears among these random variables. Now, as a real experimental example, we apply the Maze algorithm to the MNIST problem. In this experiment, we divide each image into 64 subareas, where each subarea has 36 pixels. Then we quantize each subarea to a discrete variable. And then we apply the Maze algorithm to compute the top k eigenvectors, which gives a 64 k-dimensional feature. Then we fix this feature as input to a support vector machine to train the linear classifier with the knowledge of the labels. Here we want to emphasize that the way we train the feature is without the knowledge of the label. So the process of training a feature is a unsupervised learning process. And we only use the knowledge of a label in the stage of training the linear classifier. And it turns out that for k equals to 24, the error rate of our experiment is 2%, which is comparable to a 3-layer neural networks. And we know that the way the neural network training the features is a supervised learning because they use the knowledge of a label to train the feature. In our approach, we train the features without the knowledge of labels. And we can see the performance is comparable, which shows that our approach can indeed extract important information in real problems. Finally, for general multi-analysis problems with continuous data, we could learn the common features by training deep neural networks to maximize a joint correlation loss. And the features maximize such loss should be highly correlated with each other and hence representing the common information between these multimodal data. Although we will not present the experimental results here, we believe that this neural network architecture could be useful for general multimodal data analysis problems. Okay, thank you.